let's start reading. So today we'll be covering data validation, which is chapter 4. So we'll be reading chapter 4 for the next, I would say, let's give it 50 minutes. We probably need 50 minutes to read through this, as it's about 20 pages. But it's not, it's a bunch of graphs as well, so it's not like 20 pages of text. So let's get started. Mash, if you don't mind putting up a timer, that would be really appreciated.
No problem, we'll do.
All right, so let's talk in 50 minutes. Hey guys, time's up. How's everyone doing?
Pretty good. Just to time myself, I put in roughly about 50 minutes, give or take 30 seconds. Was able to cover both the chapter as well as Google's documentation and run some of the code.
Very nice. Cool. Cool. All right, so let me start sharing my screen. Okay. All right, so today we're focusing on data validation, which is the kind of the second component in the entire ML pipelines defined here. And previously we were talking about chapter 3, data ingestion, different ways to ingest data into the pipeline or TFX pipeline. Then today we're sort of trying to validate the data in terms of schema and distribution, if it's even present, how much how much percentage of the data is missing, so on and so forth. And then next session, which is next week, we'll be talking about how do we use TFX or TensorFlow transform to process the data so that it can be ready for training, which is the next one. But we'll talk about scikit-learn pipeline right before this, because we want to try to kind of parallelly cover two frameworks at the same time for the same topics. So scikit-learn pipeline would talk about some of this stuff as well, although it's not. It's just it's more like a scikit-learn pipeline is more like a function, or a part of it. I wouldn't call it an entire framework like TFX underneath the ecosystem of TensorFlow. But it is much more customizable, I guess. And scikit-learn is probably much more widely used in many businesses. So we definitely want to cover scikit-learn for sure. So let's dive into this. And this is probably a very important topic that's pretty much not discussed in in much of the data science education, I would say. And people don't validate data because a lot of the data science projects are still using static data sets, and in research environments. So, but in production environments, you always want to validate data before you train your model on the data that's not validated. So, okay, so in TFDV is basically TensorFlow data validation. It's a package written in Python that is underneath the TensorFlow extended ecosystem. So you can use TFDV separately without using TensorFlow extended in its entirety. So yes, why data validation? Basically, you want to try to learn from patterns in data sets and generalize these learnings. And a lot of times you want to try to see, hey, do you have data anomalies? Is your data schema the same? And checking the statistics of your data sets to see if it's still aligned with the statistics from your previous training set. And we'll be talking about, how do you compare data sets with skews and drift and so on and so forth. A big topic or a very important topic is train serve skew. And that basically talks about how your training data is different from your serving data, or your training environment is different from your serving environment, therefore causing the kind of skew that would impact your model performance, which is sometimes hard to detect. If you don't try to validate your data in a methodological way like this. So any questions on this? Seeing some chats. Great. Thank you, Mesh. Yes. So
I have a general
Yeah.
comment. I'm sorry.
Yeah.
Go
ahead.
I've been just kind of going through the complete book, kind of just flipping through some pages and then looking at some topics. I've noticed that, the example used here is for a tabular kind of a data wherein we have, neat columns and uh, features. But then, like I'm working on a problem of images these days currently. So, like for example, with respect to drift, it's pretty easy if we have a tabular data wherein we can find out means, we can find out L norms, and then find out the drift. But what if the data set is of just images? How do we, just find out the drift in the data set as and when new data comes in? This is one kind of a problem that I've been facing since a couple of months. So I mean,
You
this
can
could be a
do
very
you
good
can do
opportunity.
some kind of statistics on the images, like a histogram of the pixel values. That's the most primitive thing I can think of to look at the images. And then if the histograms distributions of pixel values change appreciably, then you have some drift on your hands.
I have tried those. Tried two methods. I mean, one of them is the histogram, and then the other one was I've trained uh, I've trained a model. I've used a pre-trained BGG and then kind of fine-tuned it on my data set, and then using the feature set of the output, tried to find out the k nearest KNN means, kind of do a kind of an unsupervised way of doing stuff. But then those things are not kind of really helping me out. So I mean,
Another thing you might try is look at the Fourier transform of the image, because that will give you some measure of the spatial structure in the image. And so if you expect all your images to have similar spatial features, feature sizes and so on, and then all of a sudden you see an image that has a different distribution of sizes, then that indicates your drift.
sure, that could be a good way of doing it. Yeah. In general, I mean, this book would have been useful. I mean, much more kind of, it would add to this if we kind of also analyze some sort of images as well and see, how things would work out with this particular framework.
Yeah, I would definitely agree. And I would say, maybe there's a way to train a classifier and just let that detect the distribution of your images if you're doing image classification. If the next batch of data is, let's for example, if you're trying to classify 100 objects, and if the next batch of data is only has one class, which would mess up your model, right? And maybe just like detect that and just try to predict on that, and if it's and flag this batch of data if it's all like the same class. And then, maybe don't train on this batch. That's one way I could think of.
That could be, yes, because what I've been facing is, the classifier or what I'm trying to do is using object detection. So effectively, it's confidently kind of failing, giving me false positives. So, and the data set is pretty huge. Every week I get around 15,000 images. And then within that, I have to multiple object detections. Each image would have around 15 to 20 objects in it, and then kind of messes up everything up. Just a thought. We could kind of go through it and then see how things would turn out.
Yeah, I would definitely be interested in learning more about this in the image context. But yeah, even Google's tutorials are only based on tabular data. But that's the thing. I suspect the reason why they do that is a lot of the businesses are still dealing with tabular classification data sets, and they probably want people to use more TensorFlow with that. So
yeah, probably, yeah, because I've tried every resource, tried searching Google, Reddit, every forum possible, but couldn't really get a clear answer on clear cut solution wherein people could have found or implemented a method of finding drift in images.
Yeah, and also I would maybe think I would like contact or ping Rakil in the channel, because he deals with image data for his work. So he constantly deals with computer vision. So I'm sure he has some ideas of that. Yeah, he's more experienced in computer vision tasks than me.
Another thing you might try is take the images and scale them down to something manageable, like 128 by 128, and then flatten them, and then take dot products and see if there's a drift in the dot products. If each image is a vector, you can convert. Then if you scale down each image to 128 by 28, 128 by 128, then you can flatten it, and it has a length of 128 times 128 squared, right? And then you take the dot products of the images with each other and see how different they are. And then if you detect a large difference, then you can start to see there's drift.
Didn't they I think the book introduced or TFX uses L infinity norm. Maybe that's
the L infinity norm of an image would just be the largest absolute value pixel value. So that's not going to help very much.
The difference of it.
The largest difference, yeah, the largest absolute pixel value different. I don't think that's going to help very much.
True. Okay.
Well, one of the other ways that I could think of is like you can adding to Wenchang's comment in terms of like training a model. Possibly what you can do is also look into building something like a CNN-based autoencoder. So like, for example, you have a set of image data from a given distribution. So if you are building an autoencoder, you have some reconstruction loss. So you can define that threshold, and then you can compare against the new data set that you're getting. So if the reconstruction loss is higher than the threshold, then essentially there is some drift in the data. So that's one other way, possibly.
Okay.
That's an excellent idea. I think that's an excellent idea.
Yeah, that seems a little more intuitive and yeah.
But the only thing, the only thing might be an issue is like if you have multiple images or say multiple objects to detect in your data set, you might have to do that separately for all the objects and then do the reconstruction for each single one of them.
Yeah, that makes sense. So you'd have to build an autoencoder for each image category, maybe.
Yeah.
Yeah. That also, kind of Yeah, this sounds good.
And also know that your low dimensional should be as low as possible, because computing the reconstruction loss in as your dimension gets higher, your norm sort of degrades. So you can't, when you come when you do that, the distance metric is sort of skewed. So you might need to be careful choosing the low dimensional space.
Okay, fine. Got it. Thanks. Thank you.
Cool. All right. Thank you for the questions and answers. Wonderful stuff. Cool. So, and let's, I think this session is probably more coding, or I guess more visualization and more investigation, and rather than just concepts or yeah. So so I basically just ran through my own .py file, and again, I just compiled different, bunch of code from the book and ran through them. Maybe I should just talk about the code a little bit more. Okay, so I just created a function called CSV statistic generator, calling tfdb.generate statistics from CSV. And with that, you can generate a schema. Then you can display it, which is this table. Okay. And let's look at it quickly. So it's basically listing all the features right here and the types of it. I was trying to look it up, but I couldn't figure out how they define bytes and strings and differentiate them. And if someone found out the definitions, why some of them are bytes and some of them are strings, please let me know. And presence, obviously, if it's 100%, if it's required to be present, or if it doesn't have to be like 100%, present, and it can be optional, so meaning they could have missing values and stuff. Valency, I believe it's, let me look it up.
Much of it is required in the data set.
What's that?
How much of the feature is required in the data set to be consistent?
Yeah. For categories, it's if it basically requires at least one category, right? So that's what it is. That's what valency is. And domain, time response, product. I don't know what domain is, but that's basically what it is. You can display the schema and kind of check it out. And of course, you can do it not just with CSV files, you can do it with TF record files as well. So I kind of just compile that function really quick. Instead of doing the trim val split that the book does, which uses two command line commands, I just basically called scikit-learn trim test split, and I wanted to see if I shuffle it, I would try, then I would have, better or more consistent data distribution, and then I don't have anomalies. I want to try to avoid anomalies, basically, and that's kind of how I did it. And just shuffle split equals to true, and if I want to shuffle split, I just basically pass in shuffle equals to true with trim test split scikit-learn function, and with the test size of 0.1. That's my validation data. And of course, I want to randomize it. That's what it is. Okay. So, and then you can generate statistics with CSV, with TFDV.validate statistics. And with, you just passing the stats you generated and the schema, then you can basically see the anomalies as well. So I want to kind of go through this as well. This is pretty cool. And did everyone get a chance to play around with this? This is basically the visualization of the TFDV.visualize statistics. And when you pass in train and val data sets, it will be able to compare these two data sets. And of course, it doesn't have to be train val. It could be train serve, right? Your training data sets and your serving data set, or it could be, I don't know, your last batch data or your current batch, something like that. Basically, it's able to compare data sets in a pretty powerful way. And I'm sure you can probably do this with third-party library, but it's just nice to have this incorporated in the TFX library. So, and if you do this, basically, if you just expand this, you will see, hey, this is the numerical features, consumer distributed. I guess that's the label. And of course, I only have 10% of the validation data sets, zeros being 77% or 76%. So it is not as balanced as we want, but it's not as bad. It's not a very imbalanced data set. And we don't have any missing value. That's great. And percentage. So, and if we just expand this, this is the categorical feature, basically going through all the categorical columns: product, subproduct, issue, sub-issue, consumer complaint, narrative, company, state. Let me turn this off. Zip code, company response, timely response. So, and notice it's trying to compare two data sets with two colors, right? And it will tell you the missing values. So, and as the book kind of explains, if this is a very important feature and you have 30% of the values missing, that could be a problem. And you want to try to investigate why this is missing, right? So, and if it's not, then perhaps it's fine. So issue, we don't have missing values. And we have the top category as incorrect. I can see the full text of it. Maybe there's a way to adjust it. No. Okay. And if you hover over this graph, it's able to kind of tell you the categories, right? So false statements or representation as an issue, talking and threatening and illegal action, that's an issue, settlement process and costs, that's an issue, and also sub-issues and stuff. Consumer complaint narrative. Okay, so obviously that is that's going to be a little messy, pretty much. Okay, States, pretty consistent between two data sets. Zip codes as well. Company response. Okay, so if we do percentage, we'll see basically, hey, validation data sets closed with explanation, we got 75.9%. For training data set, we got closed with explanation, 76.3%. So very close, right? Basically, if we do percentage, then we're able to compare apples to apples and have an idea of the distribution. And timely response, yes, 96% compared to 96.8%. So for this particular case, I'm just comparing the training data set to validation data set, right? Because I want to make sure, hey, if I'm training on this set of distribution with these set of features, I don't want this to be very different for my validation data sets. Does that make sense? Okay, so this is very cool. I really liked it when I first saw it. Okay, so back to the book. And you can install TFDV or TensorFlow data validation separately with pip install this. Generate statistics, we kind of talked about this. And you're able to kind of look at this by just, print it out. Generating schema, and that's what a schema looks like. Name products, type bytes, product domain, presence, minimum fraction, 1.0 minimum count, 1, shape, dimension, size. We talked about this. So the then with everything, we've visualized the distribution and the statistics, and we want to see if there are anomalies. So we want to try to detect anomalies. Maybe some of the stuff is not very visible, or let's say you're running this pipeline in production environments, then you'll probably not be able to view this on the fly, right? So you want to make sure, hey, if it has anomalies, then stop the pipeline, and then you investigate what's going on. So this is a quick way to kind of just flag it. Hey, let's stop the pipeline. Don't let this flow to the trainer or the pusher. And let's just stop it here, basically. So that's where we detect the anomalies. Okay, so and we're basically calling tfdb.generate statistics from TF records. And validate statistics, I'm sorry. And statistics equals to validate val stats, and schema equals to schema. Basically passing in the statistics you generated from statistic gen, and pass in the schema from your schema gen, and display anomalies. So I didn't have this. It's probably because I used shuffle split. Could be the reason, I don't know. But anyone had this anomaly? No? Okay. And you're able to kind of just read the anomaly info. The key is company description. The feature was present in fewer example than expected. short description, column dropped. The feature was present in fewer examples than expected. Updating the schema. I think this is basically, you can try to customize your schema if you want to. So I'm not going to talk too much about this. Data skew and drift. And we were talking about perhaps, L infinity might not be the way to go for image, but this seems to be a great metric to use for telling the differences of your data sets or two vectors. And that's the kind of the backend metric that the skew comparator uses, and also probably the drift comparator as well. And cool. So back to the code. And I basically just compile this code in a function. And I basically just say, hey, feature name, train stats, serve stats, schema, threshold. So I can set the threshold I want and pick the feature name I want. So I don't have to rewrite the code, every time, or change, I can just change the function parameter. Okay, so and basically calling the validate statistics and passing in all the parameters, set the threshold here, and return the skew anomalies. So at least if I do want to check it, I can check it with the variable. Same thing with drift validator, but instead of serving statistics, it's previous statistics. Okay, and instead of drift skew comparator dot infinity norm dot threshold, it's the drift comparator infinity norm threshold. Okay, pretty straightforward stuff. But what's the difference between skew and drift? I think what the book has said is basically, hey, for skew comparator, you want to use it for data sets, like that are somewhat different, but not exactly different. But like basically, I would say if it's a train data set versus serve data set, then skew comparator is something that you want to use. For drift comparator, you might want to use it for data sets that are that basically only have time differences. If it's yesterday's data or 10 days ago, then compared to today's data sets, then drift comparator could be the way to go. So again, I didn't have this. I don't know if you guys were able to reproduce this anomaly, but I wasn't.
Yeah, I didn't get any anomaly either. I just get the same output. I tried different things, just says there are no anomalies in green.
Yeah, that's why I think some of the code and examples in this book are not as reproducible. Nevertheless, there are very few books on this topic, so I kind of just picked this one. So bias data set. So sometimes you want to make sure your feature distribution matches the reality, and also, hey, is it being biased against a certain gender or race, and so on and so forth. So you want to make sure, and MASH knows all about this, right? So, and you don't want to get hit with lawsuits on AI bias. MASH, do you want to chip in on this?
Sure. So this is an interesting one here, and I thought about making the very bad joke about Google, because we're working with TensorFlow ecosystem here. and how Google's gotten in trouble with having bias in a lot of their own training data sets. Everything from, like, if you were to look at images, something I even tried today, if you pull down one of Google's own image recognition models, it looks at people of various ethnic backgrounds completely differently. And you can try it on your own computer when you pull that model down. This is an example of that kind of bias. You really, and Google, and over here with this TFDV capability, it does permit engineers to dig deep, to ask the right kinds of questions to assess whether there is bias and the kinds of sociological, practical bias that one should imagine might impact the predictive model. And this is where you just have to be a little bit more smarter about it. You have to think less about predictive models, more about what is your data saying.
Right, exactly. So yeah, and many big companies had that trouble, right? They roll out a product and they found out it's racist, and they had to retract the product, right? With the case of Microsoft, Cortana, I think they found out. Yeah, I think there was an issue with Cortana from Microsoft, so they had to roll back the product. So significant costs, right? And not to mention lawsuits and stuff. So you know, in the political environment, we do want to be aware of this. So cool, but sociologically, certainly for sure, but also, you know, geographically, demographically, and the idea is that matching reality? Is that matching the reality of our current society, right? So, or, you know, that particular topic that you're focusing on. So, and here kind of the book kind of mentions a quick example. It's looking at the states, and it was basically saying Texas should have more population or bigger population than Florida, so it should be kind of ranked at second place. And if you do find bias in, you know, in your data set, it might harm your model's performance, then you probably want to go back and collect more data or under sample your data to get the correct distribution. Now, the idea is that your serving or your production data, production level data that comes in is probably the reality, right? And so if you don't have the right distribution matching the distribution of your production level data, then, you know, you have a misalignment right there, which further causes train serve skew down the road. So okay, and also talks about how you can slice data in different ways with TFDV, and I'm not going to dig too much into that. And also it talks about how to use data flow as Google's product. Again, I don't want to spend too much time on this because it's another tool and you might or might not use it. And it's certainly not a requirement to incorporate Google data flow, which is more like a dashboard product within the pipeline. So if you read it, great. And but I don't want to spend too much time on this. So cool. So now we talked about these components, and we want to try to tie them together. And basically we had this, and here I am trying to tie them together and I haven't finished it. Missing it. Okay, we're talking about example gen in the last chapter, right? Data ingestion. And now we have the statistic gen and schema gen example validator. Now we also talked about a lot of TFDV, and fortunately, I think TFDV or the example validator component detects a misalignment in the dataset statistics or schema between the new and the previous dataset. It will set the status to failed in the metadata store, and the pipeline ultimately stops. Otherwise, the pipeline moves on to the next step, the data processing. And the note here, example validator can automatically detect anomalies against the schema by using the skew and drift comparators we described previously. However, this may not cover all the potential anomalies in your data. So the idea is that, hey, this might cover some of the cases, but if you wanted to try to detect other kinds of anomalies, you want to try to write your own custom components, which we'll talk about in chapter 10. Okay. Any other questions? We are pretty much good in terms of the book material, but I do want to talk about this notebook as well, as Mash kind of paid me on this, and I originally was looking to it, but totally forgot about this. And so I kind of want to complement this with the books going forward as well. This is Google's official TFX tutorial, and but it doesn't cover all the components. Okay, so it does cover, some, one pipeline, a simple pipeline, and data validation and feature engineering and model analysis. So it covers about three components in details. Some of the insights from the book, they wouldn't touch upon, but it does have a more complete picture about what's going on, and it is TensorFlow's own tutorial, so I feel like we definitely should go through those when we have time. So any questions up to this point? I'm going to share this in the chat.
That would be next class, right? Which is more of a practical, where we can start to go through Google's code, maybe.
We have about 15 minutes left, and next class is data processing. So that's probably this one.
Okay.
That's the TensorFlow transform. So we'll be going through this notebook next class, but this one is this class. Yeah. So if you want to follow along, please open it up in Colab. I have that link. And what I like about this is it always has an end goal in your mind, meaning like it has that finish first and iterates philosophy embedded. It always gives you the entire pipeline in the end, rather than, give you just several components. Yeah. Okay, so I have this opened. And of course, for some reasons, Colab has issues with pip, so you have to restart your runtime once you install your packages. And it says right here, you must restart the runtime in order to use newly installed versions. So before you hit this, you have to reset or restart your runtime right here. Restart runtime. Then you run this cell and the following cells as well. So Give everyone 2 minutes. So this notebook is using TFX equals to 0.27.0. We're using 0.28. But 0.29 does seem to have problems. So just be aware of the version TFX. Okay, so hopefully everyone has this open up. And we're going to quickly run through this. Of course, feel free to spend more time on this because we're not going to be able to cover all the details of this notebook in 10 minutes or 15 minutes. So yeah, definitely spend time on your own playing around more with this. And this notebook does seem to have, and this is probably fairly new because I'm seeing to-dos in this notebook and also like code like this. That's just, you don't do that. You always just put it up front. And we're dealing with Penguin data sets. Again, another classification data sets. And in many data science projects, like I would say, I like to say classification is king because in the end, for many use cases, you can always convert your use case into classification somehow. Even regression tasks can be converted into classification tasks if necessary, and also recommendations, stuff like that. So, and a lot of times we are dealing with tabular data. So most data scientists don't deal with NLP or maybe a little bit NLP, but certainly not image. So most data scientists only deal with tabular data. That's the reality. So, okay. Penguin data set is basically a data set about penguins. It's and has like 4 columns or something like that. Yes, 4 features and numerical features, and we're trying to classify the species of penguins. So it's like iris, but perhaps a little more complicated. And it's about an animal. So defining some roots or paths right here, and setting the data roots within the temp file. So you don't, so basically you create a temporary directory rather than the actual directory, or, and then that's where you store your data, and you pull it from GitHub, user content, TensorFlow, penguin process.csv. This is what the data looks like. Okay. Species 0, that's probably the label. Common length, common depth, flipper length, body mass, that's self-explanatory. Common, I looked it up, it's basically, I think it's the mouth of a penguin. And so that's the length of that and the depth of that. Okay. Oh, we got 3 classes here. So 3 types of penguins. Okay. Anyone likes penguins?
Yeah, penguins are great.
No? Okay. No one likes penguins?
Yeah, love penguins. Penguins are great.
Great. Great. Okay, so thank you. And so with that, we're basically, and this kind of, again, this complements, right? So we're talking about just statistic gen, schema gen, CSV, example gen. So only up to the data validation phase. And for this simple pipeline, create schema pipeline. So this is, we define as example gen, statistic gen, and schema gen right here. And exactly the same thing as I wrote it here, right? So you could write the same thing for our consumer complaint data sets. And what you do is you want to compile them into a list called components equals to these 3 gens. And you want to feed it into the pipeline.pipeline. Now, where does this pipeline.pipeline come from? This comes from tfx.orchestration module, and you import that pipeline class. It's probably a class in pipeline.pipeline, and we specify the pipeline name and pipeline routes, and you feed it these 3 components into that, and this is the metadata connection config, and this is where you probably store the metadata for the pipeline. And now this is just 3 components. Obviously, we're going to have more components, right? We're going to have the transform or the data processing components. And also we're going to have the trainer and pusher and all the other components. But this is just demonstrating, hey, how do we put these 3 components together? And how do we run it? Basically call the tfx.orchestration.local import local.dag.runner. So this is running the pipeline. Okay, and so instead of using, remember we were using context.run in an interactive notebook to run this. So, but you don't do that as you're basically compiling every component together right here and just run it in its entirety. And you want to review the outputs of the pipeline as well, of course, and it has some helper functions, and to get artifacts and visualize the artifacts. Artifacts are basically just outputs of each steps. Okay, that's what the definition of artifacts are. And as you see, I clean up the code a little bit so that it's more readable, and I move up the imports statements all the way to the top. And also there's some to-do from here. I guess Google hasn't even finished this, and it's trying to move these functions into the TFX library, or someone hasn't deleted this comment. Okay. And with this block of code, you can pretty much get the output and artifacts and visualize them with the visualize artifacts function. And basically, it's the same thing as what we are trying to do here, right? Except we used TFDV, visualize statistics. I believe that's what it is. Let me see. Yes, tfdv.visualize statistics. But in this case, we're just using visualizations from tf.orchestration. So we're using the visualizations module from the tfx.orchestration module. So we're calling a different module. But hey, it's pretty much the same thing. And in terms of visualization, you know, again, this is numerical features. So we're all looking at counts and more so like histograms in terms of distribution. So, okay. Examining statistics, that's what we did before. Export the schema for future use, you can do that. Okay, and then it's trying to basically train an ML model from the beginning to the end. So that's why I like this. It's always, you know, trying to follow the finish first, then iterate philosophy. Basically, this is the end-to-end pipeline. And we have the input function. This basically generates features and labels for training. And we build a model here. So, you know, maybe there's some customization code that you want to put in for your model. And now we're back to like hands-on ML stuff, right? Actually building a Keras model. And we're using, let's see what model we're using. Oh, okay. This is the feature keys, this inputs, and we're just concatenating all the inputs. Okay. And for range 2, we're using 2 layers, 2 dense layers with 8 units activation ReLU. Then we have an output layer of 3 units because we have 3 classes. And then we instantiate a model. We compile that with Atom Optimizer using sparse entropy, sparse categorical cross entropy as the loss function, using the metrics, the accuracy as metrics, and we get the model.summary. Okay, then TFX trainer will call this function. So we're defining the run function first, having the train data set, the val data set, model here. So basically we're just refactoring everything into one function, then so that the trainer component will be able to call this function. And it's called rumfn. Now we have the entire pipeline definition right here. So again, example gen right here. Okay, statistic gen right here, schema gen right here, example validator, that's what these 3 are what we've been talking about today, right? This is what we talked about last week. And we'll be talking about trainer and pusher in later sessions, but it's already included here. And the trainer is calling, let's see, where is that? Run fn. Module file, generic 6 outputs example. Trainer, I don't see that. Maybe it's passed in as a parameter somewhere. Okay, but notice you always put them into a list, and just call it components. Of course, you can call it whatever you want, but it's easy to just call it components. And example gen, so compile all the components right here, train, and with the trainer, pusher, and these 3 are what we've talked about today. And then feed them into the pipeline, and, you know, passing all the list of the components right here at the end. and use the local DAG runner to run that. Now, down the road, we probably not going to be using this. We will be using Airflow or Kubeflow pipelines. So we'll be creating and defining DAGs from these two frameworks rather than just this. So, and as, yeah.
At this point, the code seems very, very specific to just TensorFlow extended. And now there are so many, I think we had this conversation in the last class or so on the side. There are so many frameworks out there. NVIDIA has their own framework. IBM with Elira also allows you to have different pipelines. My previous company, we had our own framework to kick off and orchestrate workflows. This becomes fairly specific. I mean, I think it's just making that comment that if we're here, this is specific, but then if we keep our practical coding with something generic like Airflow or Kubeflow, then
yeah, this is, yeah, exactly. So this actually is not, I mean, it's not really orchestrating it. It's just running through it, right? So you will see much more, Airflow allows you to have a much more complex orchestration and also probably Kubeflow pipelines as well. So yes, Airflow is I would say framework agnostic, and we'll see examples of Airflow down the road. So
I like that, framework agnostic.
Yeah, exactly. So because Airflow, I think we talked about that last class. Airflow not only is used for ML pipelines, it's also used for data engineering pipelines as well. It could be used probably for every sort of pipeline in tech world, but it's mostly used for data pipelines, and it could be data engineering tasks or ML pipeline tasks. So yeah. And as you can see, we have the model summary here, and we got 139 params. What was the results that we were able to achieve? We got 60%, so that's terrible. That's probably because we didn't do any epochs or something like that. We could probably do better on this if we try to spend more time on tuning the model. But I guess that's not the purpose. So, and also we didn't process any data, right? We didn't. I don't know how clean or dirty this data set is. And no anomalies. That's what it is. Cool. So this is a quick run through of the entire pipeline. But of course, we're growing this pipeline with every single tutorial. And going forward, we'll complement this with the book. I feel like that's a great way of going about this course in the future. The book does have some great stuff, but sometimes it does miss, the big picture or the full picture. Yeah. Cool. Any questions or comments before we close off? Cool. So I will take that as no. On that note, I want to thank everyone. Thank you, Mash, as well, for hosting this with me. I really appreciate it. And everyone, have a good night.
Wencheng, thank you so much. This was fantastic.
Great.
Thanks, Wencheng.
Yeah, if anyone has questions, just ping me on Slack or send in the channel, or ping me directly if you want. Doesn't matter. Okay,
All right.
bye.
Stay safe, everybody.